The probability integral transform is a technique that can convert any continuous random variable into a uniform distribution by using its own CDF, the cumulative distribution function. Because of this unique cap capability, this is also known as universality of the uniform distribution. In this video, I'll try to explain a use case of this probability integral transform. In the context of finance and risk management, this concept is especially used for model risk validation and is very superior to the VAR model. Let us try to understand why. A VAR model checks for the exceedances after a certain point and not at every quantile. Say, for example, for a confidence interval of 99%, a VAR checks if the exceedances of the worst 1%. Whereas the PIT, it checks the actual outcomes at every quantile with respect to the model. For example, if a model says that there is a 10% chance that the return is less than minus 2%, that is a loss of 2%, or if the return is less than 0%, that is there might be definitely a loss, that is 50%, and there is 90% chance that the return is less than 2%. And this is a model prediction. But actually, the return turned out to be 0%. So it essentially maps at the point of 50 percentile in the model. So the probability that the model assigned an outcome that is actually less than what happened is 50%. So the model can predict that the outcome can be -4, -2, or -3, and it can also predict that the outcome can be +2, +4, +5. So essentially, the actual outcome is 0%, but the probability that the model could have predicted an outcome of less than 0% is 50%. So that's the reason we have the PIT of 0.5. For a good model, the distribution of the predicted outcomes should actually coincide with the distribution of actual outcomes. This essentially means when we use the model for multiple predictions, 10% of the time, the outcome actually should fall in the worst 10% of the model, that is below 10th quantile. And 50% of the time, the outcomes should actually fall in the worst 50%, that is the first half of the model. And 90% of the time, the outcomes should fall in the worst 10%, that is it should be below the top 10. Hence, PIT should be uniformly distributed for a good model. For example, if the PIT is a U-shaped curve, as in the first curve, it tells us that the model outcomes likely end up in the first or last quantiles when compared to the middle quantile. To clarify, the x-axis shows the CDF. So, 40% of the time, the outcomes should be less than 40. However, the outcomes are less than 40, more than 40% of the time, because it's not uniform. In other words, say from 0 to 0.2, there are more number of outcomes when compared to 0.4 to 0.6. So, essentially, at every quantile, the outcomes are not uniform when compared to the model. And similarly, this is the inverted U shape. Even in this case, the outcomes are more concentrated at the center rather than the tail. An inverted U-shaped PIT underestimates the tail risk. So, the actual outcomes are concentrated at the edges of the CDF. For the skewed PIT, the outcomes are concentrated at the zero part of the CDF. That means the actual outcomes are much worse than the predicted outcomes. That is, the model is more optimistic. These details summarize whatever we have just discussed about the graphs. Let me show you an example, a working model from Python. In this example, x values define the outcomes of the model and x actually define the outcomes actually derived in the market. In this example, x values are actually the model outcomes, whereas x actual are the, in this example, x values are the model outcomes and y x actual are the actual outcomes in the market. If you observe, the x values are -2, 1, 4, 7, 8, 8, 9, 9, 23 and 45. And x actual are -30, -30, -25, -20, -5, +5, 23, 45, 75, 95 and 100. So they are more widely distributed, and also there are more number of extreme values when compared to the exact x values that are predicted by the model. So I have taken a discrete example without assuming any underlying distribution here for simplicity. And going further, this is the code just to have the PDF and CDF functions. The CDF values of both model and the actual outcomes are calculated just for illustration purpose. These are the values. And the PIT is calculated with the following logic. For this example, the calculated PIT comes out here this way because there are 0 x values, that is x model predicted values that are less than -30, -30 or -35. Or sorry. So because there are 0 x values that are less than these values, we put the probability as 0. Probability that the model outcome is less than actual outcome of all of these numbers is 0. Similarly, there is 0.3% probability that a model outcome is less than 5. So 5 is the actual outcome if you see here, and there are 3 values that are less than 5. So the probability that the model outcome is less than 5 is 0.3. And similarly, there are 9 outcomes that are less than or equal to 23. So the probability is 0.9. That is 9 out of 10 times the model outcome is less than 23. That is actual here. And here, when the actual outcome is 45, 75, 95 and 100, 100% of the time, the model outcome is less than these numbers. When we plot the frequency distribution of the model and the actual, we get it this way. So -2, -1, 4, 7, 8 and 9 occur twice, and then 23 and 45. So the extreme values, if you see, there are -2 and 45. Whereas the actual distribution is much wider. The extreme values are -30, that occurs twice, and -25, and then there are 195 as well. It's much wider. Also, there are much more extreme values with greater frequency. I shall not go into the depth of these details, but let me help you understand the frequency distribution. So these are the model outcomes. So -2 occurs once, 1 occurs once, 4, 7, 8 occurs twice, and 9 occurs twice. So this is the frequency distribution of the model outcome. And when we take the CDF of this function, we have it coming out to be this way. So taking only the top points, then we can plot the CDF. And PIT distribution is coming out this way. So this is essentially the numbers that we actually calculated above. So there are 4 values at 0, 0.3, 0.9, and again 4 values at 1. So 4 values at 0, and 0.3, 0.9, and 4 values at 1. Essentially, if you take the PIT distribution, if you turn this around, it's almost in the U shape. It's not uniformly distributed. This is as predicted because we see more extreme values in the actual outcomes when compared to the model. When we take out the CDF of it, the uniform distribution CDF should have the 45 degrees. Whereas here we have more extreme values. And this explains that the model is not exactly representing the actual outcomes. To help you understand, instead of actual outcomes in a different distribution, if we instead take the actual outcomes are same as the model outcomes. Let's see what happens to the code. Okay. The CDF distributions are same for both actual and the model. And PIT distribution is uniform almost. So expected, we have the PIT distribution uniform, and it's very close to the 45 degrees line, the PIT CDF. We essentially see 2 points at 0.8 and it doesn't look normal, but if we take large number of data sets, we have equal number of x values. I mean, the frequency of x is almost same at each and every point of CDF. Let me show you by inverting this. Say for example, the model outcomes are much more wider, whereas the actual outcomes are concentrated or have lesser range. Yes, here the PIT is concentrated. It's an inverted U shape, as we already discussed before. And it's not normal, since it's not normally distributed, it's deviating much higher to the normal distribution CDF, and the model is actually overestimating the tail risk, whereas there is not much tail risk in the actual outcomes.